So it's our last colloquium of the year, so thank you in advance for all that came regularly to this. So, because it's the last, we have I think the most recent professor in the department.
I think so,
Richard.
yeah.
Okay, so Richard Brito has joined the department as a professor this year. I'm right, yes.
Yeah.
But he has a very long connection to our department. He was a student here, a PhD student here, where he received the prize for his thesis, as far as it says here.
Yeah.
He then went first to Potsdam, then to Rome, and came back with one of these FCT contracts of 6 years that don't exist anymore. And now has a job for life, which is something we should always congratulate people for having. And so I don't understand much of what Richard does, but there is this thing that I find very appealing, and that has been also common in some of the later colloquia that we have, is that his work sits at an intersection between two fields. In his case, between cosmology, gravitation, and particle physics. So the floor is yours.
Thank you. Thank you, and hello everyone, and thank you for coming to this last colloquium. So as Guillermo was saying, so I did a PhD here. At the time I was doing the PhD, I was working on stuff that I'm going to speak about as well. So these some of the things that I will speak about, I've been working for quite some time now. But specifically this last part on gravitational waves was something I almost didn't do anything during my PhD, but then something happened exactly at the end of my PhD, which was the first gravitational event was detected, and it kind of completely changed the path of my career completely. And so nowadays a lot of what I do are related to gravitational waves, as I will explain. So to give you an idea of what I will speak about, so I'm going to spend, at least in my plan, was a bit less than half of the talk. I hope I don't go above time, but the idea was to give you an overview of the past, the future, and the past, the present, and the future of gravitational observations, to give you an idea where we stand now and where we are going. And then I'm going to talk about exactly the subject of some of the work I do, in particular this idea of using gravitational observations and black hole observations to actually detect new particles or constrain their existence. So I'm going to explain a bit about studying massive bosons, which are basically bosonic particles in black hole spacetimes. So how they interact when you have what happens when you have these particles around black holes. And I'm going to tell you something about ways that we could in principle observe very light, extremely light particles, if they exist in nature, using gravitational observations. But before going there, let me then start by remembering this gravitational event that happened. So it's going to be exactly 10 years in 3 months from now. For those of you that will be here, there's going to be a celebration actually on the 13th of September in Pavillon Ciência Viva that we are organizing to celebrate these events, the 10 years of these events. So you're all invited to come. You'll probably see announcements when we have more concrete plans for it. But we are working on it. So as you probably all know, so there was this event this gravitational event that was detected 10 years ago. So what was actually seen was basically two big black holes with roughly around 30 solar masses of the sun each, that basically merge and basically produce some signal that I will try to explain in a very brief short sentence what exactly was that LIGO was seen. And actually, I went back to the cover of Público. So those that are not Portuguese, this is one of the main Portuguese newspaper. And I think here you cannot see it, but in the logo of Público, there's actually small wiggles that I only noticed now coming back to the logo, which I think was a very cool thing to do. I haven't seen Público change their logo for anything else besides probably this discovery, which shows really the importance that this discovery had. But coming back to the origin, so what exactly are gravitational waves? I'm going to explain in one sentence that I took from this website. So it's the website of the LIGO collaboration. That basically says that gravitational waves are ripples, so they are perturbations of space-time. So space-time is essentially, according to the theory of general relativity, space-time is not something fixed, absolute. It's something that can be curved basically by bodies. And gravitational waves are basically just small perturbations that propagating on these, basically are perturbations of space-time itself that propagate at the speed of light. And they are basically produced, because they are very weak, to see them, basically what we can see are basically among the most violent processes that happen in the universe. In particular, basically two big black holes colliding with each other. This was predicted by, basically the first paper on this subject was by Einstein back in 1916, which is funny because it's almost exactly 100 years before the first gravitational event. The whole story of gravitational waves, the way the theory developed is also quite interesting. I'm not going through it, but it went through ups and downs. Einstein first wrote this paper and then thought these calculations, these gravitational waves were not something physical. It was just, there was what we call, it was just a gauge artifact, which means they're not really physical. But then only in the 50s, 60s, of course, people kind of stopped working on gravity for a long time, because in the 30s and 40s, I don't think I need to tell you what was happening, and so people were not really working on this subject. But then in the 50s, 60s, people started being interested again in gravity, and they put solid grounds onto the theory of gravitational waves and showed that gravitational waves are a real thing, and so people started to be interested actually in detecting them. Of course, the technology wasn't there to detect gravitational waves back in the 60s, so it took up to 2015 to actually have the technology to do it. But to basically, so what LIGO has seen was basically something like this, so some two black holes merging that perturb space-time in a very specific way, and at the end of all this process, one single black hole is formed, and you have these waves traveling until us and then going quiet after the merger. And so the way, in a very simplistic way, the way LIGO does these detections is basically by building giant Michelson interferometers that you probably have used in your lab courses. And the idea is basically, in the absence of any gravitational wave, to have your interferometer in such a way that the arms are exactly the same length, and you send some lasers in such a way that they meet at some point at some detector, where they are basically the waves that traveled from this emitter up to some mirror is reflected back. There's another laser part of the laser that there's a beam splitter here in the middle that splits this beam, goes up, is reflected in this mirror, goes back, and when these two lasers meet, if there's no gravitational wave, basically they are completely out of phase, and so there's a detector here where you will not detect anything. Of course, there's noise, but in a perfect world, basically these two lasers will completely basically be completely out of phase, such that you will not see any interference in any interference pattern. If there's a wave, what happens is basically that what the gravitational wave does is basically shrinking space in one direction and elongating in the other direction in such a way that the waves travel different paths. The lasers, travel different paths in this direction and this direction. So when they meet again, they're out of phase, and it's actually in the interference pattern that you detect. You can detect your gravitational wave. The fact that there was a gravitational wave there. And the reason why you can do that, you can do this detection, is because laser technology is extremely powerful, so we can do these measurements very well. Don't ask me a lot about this because I'm not an experimentalist. So there's a lot of details there. I don't know how to explain very well. But to tell you, so this first gravitational event was already 10 years ago, and perhaps you haven't been following much what has been happening since then. So it's been 10 years, and of course a lot has happened. And so there's been basically 4 observation runs. We are in the 4th one. So we are in this, what is here, it's called 04, if you can see it. So you cannot see it very well. This is basically year. So the first observing run, which is here, was around 2016, 15, 16, was when the first gravitational event was detected. Then there was another two observing runs, 03 and 02 and 04, where basically besides LIGO, so LIGO are basically in reality is 2 detectors. They are both in the US, so 2 detectors of the style I explained before. Of course, a bit more complicated than that, but they are both in the US. There's another detector in Italy, so called Virgo, which is slightly, actually much less sensitive to LIGO, but it still helps in detecting some of the events. It's actually useful to have a lot of detectors because that allows you to pinpoint where the event is coming from by triangulation, essentially, very well by having a network of detectors around the Earth. There's another detector called Kagra that was built in Japan. It's already in operation, but in this, for example, in the 3rd observing run, which happened around 2021, if I remember correctly, it was really just experimenting where it works. It was really not useful. It was supposed to be much better this year, but there was an earthquake in Japan, a big earthquake that completely destabilized the whole detector. So the detector from most of these 04 observing run has been basically almost offline. In principle, it will be online now until the end of 04, which should end roughly in November. And there are plans to continue. There will in November this year, so the detectors will stop, and there are plans to upgrade these detectors until 05. That should happen in principle 2028 roughly, and where basically sensitivity will double. What does it mean to double the sensitivity? It means basically way more gravitational waves that we detect. So just to give you an idea, so in 01 we had detected basically around 3 events, 3, 4, I don't remember exactly. And right now, until 03, we had 90 additional events that were confirmed. Most of them are binary black hole systems. I will show you a plot where you can see why we say they are binary black holes. There's some that, at least 2 that seem to be from binary neutron stars. There are actually 1 binary neutron star where we detected a coincident electromagnetic counterpart, so which seems to indicate it's really a binary neutron star. And there's also a couple, like 2 or 3, I don't remember, binaries which are a black hole plus a neutron star that merge. And so this plot shows you basically the cumulative number of detections as a function of time and you see that when you increase sensitivity, so when you double, for example, sensitivity, you start getting way more events. And for example, in 04, so the observing run that is happening right now, there's already been 100 additional events in roughly a year that this has been going on. So it's already the same amount of events that as was observed in the other 3 observing runs. And that's because sensitivity has doubled. And when you do that, basically, if you think about the volume that you can see in the universe, right? You increase your sensitivity, you get access to a bigger volume of the universe that you can see. And so you see, you can see way more events, right? Because there's way more galaxies inside this volume, so way more possibilities that there's some binary black holes, for example, merging. So this up to 03, so this is only up to the 3rd observing run, because of 04 right now they haven't published the results. We know the candidates because this is public, but they haven't published actually the date. So when I say candidate, it means they haven't been confirmed they are real events, because you need to do analysis. You need to analyze this data to make sure that what you see is actually a gravitational event and not something else, and not some noise, for example. And basically, this plot is something that you can. This is not very good, but if you can see what is written here, if you are interested, you can go to this website. You can actually play around with parameters and do these plots. Where, for example, here I plotted the mass of the binary systems. So this is the primary mass, so it's the mass of one of the black holes, or of one of the objects, and this is the secondary mass, which means is, of course, normally you have the masses of the two in the binary are not the same, and you call them primary, meaning primary means the heaviest one, and secondary means the one that has the lowest mass. So most of them are actually close to equal mass ratio. Not quite, but most of the events we have seen are close to mass ratio. And you see that we've seen events, for example, where the primary mass and the secondary mass are extremely heavy, like 100 solar masses. It's a puzzle because just from stellar evolution, in principle, you should not have any, from collapse of stars, you should not have any black holes formed between roughly 50 solar masses to 120 solar masses roughly, because there's something called the peri-instability supernova that makes it impossible to form these black holes just from collapse. Of course, you can form heavy black holes by just merging them, right? You take 2 solar mass black holes, you merge them, it becomes a 20 solar mass, and if you merge them many times, it becomes heavier and heavier. Of course, the probability that you see something that has merged many times becomes lower and lower the more, more times you need them to merge, right? Because it takes a lot of time to take 2 objects, 2 black holes. Gravitational radiation is basically what makes these orbits shrink, but this is a very extremely weak process. So if 2 objects like the Earth and the Sun, we will never merge until the end of the universe, basically, because gravitational radiation that the Earth and the Sun are emitting is not really sufficiently strong to actually make this system collapse onto itself. So there's already quite interesting results. We see these events. They are probably coming from events, as I say, that previous mergers that eventually merge again, but that eventually, a remnant of a merger that capture another black hole and merge again. Exactly how this happens is a whole business, right? There's a whole, this is quite interesting for astrophysics to understand the evolution of these binary black holes. That's not what I will talk about. This was to give you an idea of what we have seen. We have also seen very low mass events. So the ones that we say that are binary neutron stars, they are basically the ones sitting in this region. So they have masses that are on 2 solar masses. There's some that I said were binary black holes with a neutron star, which black hole plus neutron star, which are these ones here. There's actually one that I think is around here. Well, these ones, one is from this year, is actually from 04, that has already been published, which is actually quite puzzling because it starts sitting in this region, which here it's called the mass gap, which is not certain whether it's there or not. But observationally in the past, it was seen that there seems to be a gap between the heaviest neutron star and the lowest mass black hole, between roughly 2 and 5 solar masses. Whether it's not clear if actually you should not have any black hole between 2 solar masses and 5 solar masses. You could have actually in principle. But in some astrophysical models, you have a gap there. But you're starting to see actually black holes exactly in this region, which puts into question some astrophysical models, and people are working on it. But so this is the current state of affairs. As I say, there will be more observing runs for LIGO, but this is not the end of it, right? I mean, I think gravitational wave science will be here for quite a while, probably 20, 30 years. Until we reach a level where perhaps we cannot do anything anymore. But at least for a couple of decades, I think this will be a very, a growing field there where a lot will happen. And one of the reasons is because there's already next generation detectors being planned that will be way more sensitive than the current detectors. So the idea is, right now, for example, we detect around 100 events in a year. So every couple of days we detect an event. The idea with these detectors that I will explain is to detect basically events every second, if you want. So for example, there will be detectors on the ground that are being planned, which one of them is called the Einstein Telescope, the other Cosmic Explorer. The Einstein Telescope is a mission that is being planned in Europe, while the Cosmic Explorer is in the US. To give you an idea of scales, you cannot see it very well, but LIGO, so the size of LIGO is basically these. So these 4 kilometers, the arms of LIGO are around 4 kilometers. The idea for Cosmic Explorer is to build something where the arms is kind of a big LIGO. The arms are around 40 kilometers each, so it's a really huge thing. It's so big that actually from what I've heard, you need to take into account the curvature of the Earth when you send your laser. That's what I've heard. I don't know if it's real or not. The Einstein telescope is actually not clear if it's going to be like the L configuration. The original plan was to do a triangular configuration underground. The reason to go underground is to lower the noise from the shaking of the Earth, basically. But there's also the idea of making a triangular detector, because with triangular detector, in principle, you could even just build one detector in one place and make it effectively two detectors by having a triangle, because you can make different paths with these lasers, and these would, in principle, be cheaper to build. But these detectors could even detect, more than millions of events or tens of thousands of events. So it's really another scale that you will be talking about. There's a problem, but there's a problem with ground-based detectors. There's something that we cannot really do apart. One thing is finite size, right? You're building 40 kilometers is already huge. And if you think about in terms of frequencies, there's a limit. If you want to go to very, very low frequencies, you need to build bigger and bigger arms, because you need your wave to fit inside your detector if you want. So if you want to have very low frequencies, you need to go to very large arms. But there's also another problem, is that the Earth is basically very loud. So there's seismic noise. But there's also just a time-dependent gravitational field of the Earth, just things moving, if you want, inside the Earth. And these are affect mainly the low-frequency part, the sensitivity to low frequency around 10 Hertz. And it makes it impossible, no matter what you do, there's no detector that will allow you on Earth that will allow you to detect any wave, gravitational wave that has frequencies lower than around 5 Hertz. So the idea, and is an idea that goes back to the end of the 80s, beginning of the 90s, is to actually go to space. Because in space, nothing is shaking, it's really almost perfect. There's almost no noise. Of course, there's some noise, but there's almost no noise. And you can build huge detectors. So this is the idea of LISA. So it stands for laser interferometer space antenna. And the arms of these, it will be in a triangular shape. The arms of these detectors will be around 2.5 billion kilometers, so these are really huge arms. It will basically sit in one of the Lagrangian points of the Earth and the Sun and follow the orbit of the Earth. And this detector is not only science fiction, it actually has been adopted last year by ESA, so people have been working on building a science case and making this something robust. And ESA has actually adopted this mission to launch in 2035. So people now are actually actively working on building this and actually launching it. So now I think this, for those of you, probably a lot of you are not old enough, even not me, but when I was in high school, I think that's the first time I've heard about this, because I like to read popular science articles. They say LISA will be for 2010 or something like that. And it's been postponing forever, basically. But I think this time is for real. Although, given the political situation in the US, NASA is also involved. We don't know for sure, but because it's mainly a ESA mission, an European mission, I think it will go ahead. But, well, that said, why do we want to have this whole set of detectors, detectors in space, detectors on the ground? Well, the main reason, as I said, is because going to space allows you to detect very low frequency waves, and that's kind of like what you do with electromagnetic wave, right? You do observations in the optical, in the infrared, in the gamma rays, X-rays, radio, etc. Because by looking at different frequencies, you see different things, right? Here it's very similar. So the idea is that, for example, LIGO, the type of object sources that LIGO can see are essentially binary black holes, binary neutron stars, and binary black holes that have around tens of solar masses. And it has to do with the size of the type of frequencies that you see. If you go to very low frequencies, what you start seeing are basically not tens of solar mass black holes, but black holes that have millions of solar masses. So we know a couple of black holes like that. We know at least one that is very close by. There's a black hole exactly with 1 million solar mass at the center of the Milky Way, for example. So we will basically, with LISA, be seeing these objects, these binaries, but of two black holes, for example, that have millions of solar masses, but also something that I will talk about. Also, we will be seeing, for example, cases where you have a small 10 solar mass black hole orbiting, for example, a black hole with millions of solar mass. These objects, as I will explain, these sources, as I will explain, are quite interesting. Something I didn't discuss, and I will not discuss here, but I wanted to point out as well, is that there's actually another way to detect gravitational waves called pulsar timing array, where you use observation of pulsars to actually detect gravitational waves. I'm not going to explain how this works, but if you want, you can read about it. And in this case, you are sensitive to much lower frequencies, and so much larger mass black holes. So you go to really 10 to the 9 solar mass black holes. So these are basically the heaviest black holes that we know about in the universe. And in principle, well, for example, when I was a PhD, there was a claim that there was detection of gravitational waves in the cosmic microwave background. Turned out not to be real, but with these, if there's in principle imprints of primordial gravitational waves in the cosmic microwave background, if we become sensitive enough, we could detect gravitational waves from the primordial universe, which will be amazing. Okay, so now to the subject of this talk. So this was the first part. Now the second, just to put you into context. The second part, I want to actually say about something about. You can do, of course, astrophysics with these detections, and honestly, that's the main use of gravitational waves. No one is spending millions to do fundamental physics because that's very risky. But of course, we can get a lot of interesting fundamental physics from this. So we put together. So this is an article that was done by the LISA Fundamental Physics Working Group, on which I am part of, where we it's a review of different fundamental physics questions that we can try to answer with gravitational waves, or at least help to answer. And so this diagram kind of, I'm not going to explain everything, but the main idea is that essentially because gravity kind of links to a lot of problems in physics, it's only natural that it's actually through the gravitational interaction that you might find an answer for a lot of the problems, like, for example, dark matter, dark energy, quantum gravity, etc. So I'm gonna focus on a part that is related to the dark matter problem, so detecting particles that could explain dark matter. But I wanted to, so you can read this and have an idea, but I wanted to at least emphasize that anything that I will say is idealistic in some sense, because a lot of our work is getting basically better models, right? It's basically, we want to do precision physics, so we need to do a lot of work to basically get the best models we can, and basically to avoid things like having systematics in the measurements. And that's quite important, because with the type of sources, with gravitational waves, something important that you can make extremely precise. If you lower the noise, for example, in going into space, you will lower the noise. The type of measurements in principle that you can make will be really, really precise. So at the level, for example, of what has been done with the cosmic microwave background, which are extremely precise measurements as well. And so, for example, if you look at a gravitational wave from a binary black hole, you can start basically dissecting this gravitational wave, try to learn exactly the type of information that this wave is telling you. And so I'm going to here briefly, for example, from this type of gravitational waves, what you could learn. So this is a typical gravitational wave from a binary black hole merger, for example. And essentially, so this is here divided in 3 phases. So each phase basically has different information inside it. If you start, for example, the binary starts very early, right, where the objects are very far apart. If you think about it, when the objects are very far apart, you're basically almost at the Newtonian limit, right? So the objects where if you can remember your Newtonian mechanics, you don't care about really almost the structure of the planets, for example, of the objects in your binary. So they basically behave like point particles, right? You don't know much. You cannot really detect anything about this structure. So in the very early spiral, you basically are just point particles orbiting each other. So the type of questions you can ask there is basically things like, is the orbital decay, so as the decay happens, the frequency of this wave goes up, and through this evolution of the frequency, you can learn things like whether the orbital decay is consistent with what general relativity predicts. But there are also another questions which I'm emphasizing here because that's something I will want to talk about, is you can also learn, for example, whether these objects, this binary is moving in almost vacuum, so almost nothing around it, or there's something else here. I'm going to make a connection here with basically the dark matter problem. But if you go later in the spiral, basically as the objects go closer, you start seeing basically the structure. So for example, they can be tidally deformed. You can see their spin, the fact that they have some angular momentum. But you can also see things like the quadrupolar moment, etc. That gives you information about basically how this object looks like. So you can start distinguishing, for example, about whether this is a black hole, whether it's a neutron star, or whether it's something more exotic, some object we have never seen before, for example. Later on, basically, you have the merger. In the merger, everything becomes crazy, so I'm not going to say anything about it, because you basically you need to simulate these in the large computers to actually know anything about the merger. So I'm going to focus here only in this ring down part, which is the latest part where the black holes merge, and then you have a ring down. Ring down is basically, if you want the final object settling to some final states, so some final black hole, for example. And you can ask questions whether, for example, this ringing, so this final ring down of in your wave, is actually something consistent with a black hole, for example, in general relativity. Or if it, for example, if it was a neutron star, for example, at the end, this will look quite different, so as to give an example. A non-exotic example. But so in terms of black holes, why can we actually say all of this? And there's a reason. And the main reason is because perhaps that's not the way you see black holes, but there's something about black holes that makes it that we can actually make precise predictions with them and eventually precise measurements. Is that black holes are actually extremely simple. And this all comes back to a theorem from starting from some works in the 70s, that basically tells you that according to the general relativity, within general relativity, the unique stationary asymptotically flat, if you don't know what that means, it's not very important, vacuum black hole solution of general relativity is the Kerr spacetime. So the Kerr spacetime is basically what this formula is telling you about, for those of you that know what it is, good for you. For those that don't know, it's not important. The only thing I wanted to show here is how simple this is. I can put this in a slide. So I'm describing basically a black hole by putting one equation in the first line of my slide. So that's what I mean by being extremely simple. And there's essentially only two parameters here. So there's basically a mass that gives you the mass of the black hole and something that gives you the spin of the black hole, so how fast the black hole is rotating. So to put into words what basically Chandra Zecher, that's a person that won the Nobel Prize in 86, I think, that he basically put this, he said it very beautifully. According to him, that was actually, this is in one of the quotes that is in the physics department, I think one of the first ones. He basically said that this was, this fact that the exact representation of untold number of black holes in the universe can be represented by the Kerr solution, by this very simple equation, is something quite amazing. And so what I'm going to say now relies on that, relies on the fact that I have control. I have something simple I can work with, and now I will explain to you how I can do particle physics in principle with this. But I can do it because I have something simple, in principle, mathematically simple. So black holes are not exactly sometimes what people talk about. They are not something just sitting there like a vacuum, something like absorbing basically everything. There's something that black holes can do which is sometimes not intuitive to think about, which is the fact that black holes actually can work as batteries, essentially. So you can actually extract energy from a black hole that is spinning. So if a black hole is spinning, you can actually extract energy from it. This is something that was discovered in the, so first written down in 1969 by Roger Penrose, where he basically, in the original idea, he thought about particles colliding close to the black hole and extracting energy using particle collisions. I'm going to give you a picture, this very simple idea here, which is there's a region around the black hole where basically anything is obliged to co-rotate the black hole. It's called the ergo region. So you have the horizon of the black hole. Around it, there's a finite region where anything that is a spaceship inside this region will be obliged, the rotation, the dragging of the spacetime is so strong that the spaceship is obliged to co-rotate with the black hole. No matter how much the spaceship tries to go in the other way, it will always co-rotate with the black hole. That's something that happens only around, basically only around the black hole. So whenever there's this region called the ergo region. And so imagine that you put, like here I have this magnetic, this image. I built some shafts. I put this ring around the black hole, and I put the ring inside this ergo region. And I put some coils here. And so if I do that, necessarily, so this magnetic field, no matter how much force I put on the other direction, this image will necessarily start to rotate. There's no other way. Basically, no matter how much force you put, there's nothing else can happen. And so this rotation basically will create, time-varying flux, and from electromagnetism, this will create some currents in this wire and light the bulb. Basically, what happened in this process is, of course, the light in the bulb, so the energy that went to the bulb, had to come from somewhere, right? So it came essentially from the so the rotational energy of the black hole. So in the process, basically, you're extracting energy from the black hole. It's actually a nice way to do that also with waves that I'm going to use later on, where basically you can scatter waves. So for example, an electromagnetic wave or a gravitational wave around the black hole. And imagine that you have a monochromatic wave with some m here. Think about the spherical harmonic, so it gives you basically the azimuthal dependence of your wave. So omega m here, you can think about this as the angular velocity of this wave. So this wave is actually has some angular momentum. And so as you scatter this wave in the black hole, it goes into the region, it scatters away because the black hole has some potential, it reflects part of these waves. And if you have some detector here to detect this monochromatic wave, what you will see in case the wave has very low frequencies, meaning it has an angular velocity that is smaller than the angular velocity of the black hole, then what you will see is that this wave actually came out with a bigger energy than what it came in. And so this is called black hole superradiance. And in the process, basically what happened is that you extracted energy and angular momentum from the black hole. So now I'm going to use that to finally reach this part of massive bosons, or massive particles in black hole spacetimes. And I'm going to go back to almost your quantum mechanics classes, but I'm going to use for perhaps some of you, I don't know, I think most of you probably have seen the Klein-Gordon equation already. So it's a relativistic, if you want, a generalization of Schrödinger's equation, which describes basically, it's an equation for which any spin zero particle, that describes any spin zero particle. In this case, it's a particle that only has a mass term. So basically this particle here is not interacting with any other particle in this example. And this mu here is basically related to the mass of your boson, or you can think about it as mu as the inverse of the Compton wavelength. And something that happens when you do that, you write this equation where here this box, you write it in the spacetime of a Kerr black hole, of a spinning black hole. You can actually do a nice trick where you can separate the field, your equations, and find a single radial equation that describes your scalar field with an effective potential that looks essentially like this one for some choice of the parameters. And you might notice here there's a sort of potential well, right, where you can trap basically bond states, as you've probably learned from quantum mechanics. To give an idea of numbers, so here I'm going to work always in these units that are g, the Newton's constant, and the velocity of light are equal to 1. So if you don't, so this mu here, if you put back units, it's basically the ratio between the gravitational radius and the Compton wavelength. Which if you put some numbers for a 10 to the 6 solar mass black hole and a 10 to the minus 17, notice the very small number, 17 electron volt particle, this will be around 0.1. This will be important later on, so keep in mind these numbers. So essentially you have this bond state, this potential well, and so this is a problem very similar to the Schrodinger, to a hydrogen atom. There's a difference between these and the hydrogen atom, of course. One of them is, of course, you're talking about black holes and not atoms. But also in terms of mathematics, there's different boundary conditions, essentially. There's an horizon. So if the hydrogen atom, in reality, what you do normally is your field basically is regular both at infinity and at the origin. Here there's necessarily waves falling inside to the black hole that change the boundary conditions. And there's also no Pauli exclusion principle for bosons, which means I can, in principle, have bond states that can be extremely massive. Unlike, because I can put any number of bosons I want in a given state. So if you do this, you pose your boundary conditions, you do exactly the same kind of math here to get accurate numbers, things you need to do them numerically. You cannot, you cannot do them analytically. You get exactly like the Schrodinger, the hydrogen atom problem. You get a set of energy states, if you want, eigenfrequencies. So but unlike the hydrogen atom, first of all, because this is a Klein-Gordon equation, there's relativistic correction. So this term here, if you go back to quantum mechanics, that's basically the same spectrum as the hydrogen atom. There's correction to this term because of relativistic corrections and also correction due to the spin of the black hole. But because of the boundary condition, the horizon, there's also an imaginary part. This imaginary part basically is telling you that your bond state, in principle, is not a real bond state. It's actually either decaying over time, which is what you would expect, just because if you put a wave, there's an horizon, you would expect that this wave eventually will dissipate, right? Actually, it's not necessarily the case here if the black hole is rotating. And what you find for the imaginary part is actually it's proportional to this term. So this term is, I remind you that omega is the rotation, the angular velocity of the black hole. And if you think about what I've written before, you can actually see that when a real part of your frequency is smaller than this quantity, this is basically what I've wrote for this superradiance, the condition to have this superradiant effect. You actually have a positive and imaginary part. If you look at your field, this means that basically your scalar field is growing exponentially in time. This indicates an instability, essentially. It indicates that if you have a small fluctuation of this field around the black hole, this will not just decay eventually to nothing. This field necessarily grows over time, right? And so something must be happening. So there's basically an instability in the system. And what is driving this instability is essentially energy extraction due to superradiance. However, if you compute the time scale, this is really only relevant for extremely light fields. If you think about black holes that we know exist in the universe, which we know exist, we know there are black holes between roughly 14 solar mass, 5 solar mass, roughly up to 10 to the 10. And so if you plug in the numbers here, it means that in terms of the masses, because you want this condition to be satisfied, you're thinking about particles between roughly 10 to the minus 10 electron volt and 10 to the minus 20 electron volt. If you look back at the standard model, there's not such particle in the standard model, which means it's a reason why you probably don't know about this, right? There's no standard model particle that actually can make a black hole unstable. However, and that's the part where the ultralight bosons come in, there's proposals for extremely light bosons. The first example is basically something called the axion that was proposed in around 1971. I don't remember exactly the date, but around in the 70s. to solve a problem in QCD. And since then, it has been understood that these actions can also actually arise, for example, from string theory. There's actually in string theory predicts basically all particles you want if you can play with it and make almost anything you want. But what is interesting is that it also been shown that these particles could actually be a good candidate for dark matter, even though they are very light. And we're talking about, again, between 10 to, so these particles in principle could have any mass, but in terms of the instabilities I'm talking about, this is especially relevant in this mass range. And in the case where these ultralight bosons couple very weakly to matter, especially if you're talking about dark matter, where the only thing we know about dark matter is that it interacts, of course, gravitationally, because we've observed that, but we've never seen any dark matter candidate interacting with standard model particles. So, there's basically, as far as we know, dark matter doesn't interact at all with standard model particles. Of course, it might be not very natural, but that's the only thing we know is that it interacts gravitationally. And what's cool about this is that in principle, the effects I'm talking about are purely gravitational. So they don't really depend on couplings to standard model particles. So even if you don't detect anything on Earth, for example, in the lab, these will happen necessarily if these fields exist in nature. So there will be this instability if fields in this mass range exist in nature. And again, this has to be bosons. It doesn't happen for fermions. You can ask me questions if you want. Okay, so I took longer than I wanted, so I have to go. I want to now to tell you about a bit about what does this actually mean for observations. So the only thing I told you is that there's an instability that makes the field grow exponentially in time, and I told you that this instability is driven by extraction of rotational energy from the black hole. So what this means essentially, as the field grows in time, you're actually spinning down the black hole. And if you look down at this condition that I had here, this means that this capital omega here, rotational energy of the black hole, goes down. So at some point, this condition here is not satisfied anymore. You get a sort of saturation. So it's basically, and this is a sort of actually tidal locking. You have your wave with some angular momentum. It basically extracts energy from the black hole. And at some point, the wave and the black hole are basically kind of co-rotating with each other. And so at the end of the day, you form some large boson condensate around these black holes. So then we call them black hole boson clouds or gravitational atoms as well. However, this doesn't sit there forever. These condensates are actually oscillating in time because, well, there's some frequency related to these bond states, which makes basically gravitational wave emission necessary. So basically, these bond states that you form are always non-spherically symmetric and are time dependent. For those of you that had learned anything about gravitational waves, this necessarily means that you have the condensates will slowly dissipate over time due to gravitational emission. So if you want, in particle physics, for the people there's been works on the particle physics side of this, and the idea is that the bosons inside these clouds are basically annihilating each other and creating gravitational waves, gravitons if you want. So that's the particle physics idea behind it. The time scales, that's the part where actually it's important that you have these certain conditions in the mass of the boson, is because if you want your time scales to be, astrophysically relevant, you need basically this mu that I was saying to be around 0.1, between 0.1 and 1 roughly. And for this case, you can have, the instability can be actually quite fast in astrophysical sense. So this is a case where it will take 30 years, for example, for the instability to happen. So it's a very short time scale. But then the gravitational emission is something that happens for extremely long time scale. And so this is basically a simulation that was done by realists, where basically depicts this emission of gravitational wave. And these gravitational waves are occurring, the time scale over which this emission is happening is, in this case, for example, 10 to the 5 years, so almost 1 million years. And these are very different timescales from the events that LIGO has seen. LIGO has seen events that last for milliseconds. Here I'm talking something that, in terms of observation, it will last forever, right? Because none of us will live for a million years. So there's this effect, and in addition, the frequency of this gravitational wave is basically related to the mass of the boson through this relation, essentially. So for different masses of the boson, there will be different frequencies, and that will mean that you will detect, depending on this, if you have LIGO at very low frequencies, you will detect bosons that are extremely light, so around 10 to the minus 17 electron volt. If for LIGO, you will detect bosons around 10 to the 13. I had a plot here of the density as a function of the radius of these clouds, and I wanted just to compare, which you cannot see very well, which is this curve here, to compare against a typical density of an accretion disk around black holes, just to tell you that this actually, with respect to accretion disk, this can be extremely dense environments. I wanted to tell you that because I wanted to go to something that I will basically have 5 minutes to talk about. Keep that in mind. These gravitational waves that I was talking about, that are actually being actively searched by the LIGO Virgo collaboration. There's already been, actually, of course, LIGO hasn't detected any of these. The main reason, so of course, if it had detected, you would have heard about it, of course. But from the lack of detection, you can already do some science. You can say that in principle, there's no bosons around these 10 to the minus 13, 10 to the minus 12 electron volt, roughly. Because this roughly corresponds to the band at which LIGO, in terms of frequencies, that LIGO is sensitive to. Okay, I'm going to jump directly to this slide because that's the part that actually I've been working most lately. I've left it to the end, to the really, in 5 minutes, I think. Which I think is quite cool, which is, I've told you that you can form these clouds. They can be extremely dense. And so if you think about, you have a binary system moving in a very dense environment, of course this will change the dynamics of your system if the environment is extremely dense, right? Because as you move, you perturb your system, you perturb your environment, and these perturbations back react basically on the orbit and kind of, they can, for example, slow down the orbit, basically the velocity at which you orbit. So there's a sort of effective force acting on the binary, because if you have a very dense environment or a binary system. This is not relativistic, actually. This is one reason why, for example, there's mass segregation in there's a lot of mass that tends to go towards the center of the galaxy. It's actually related to these sort of effects. So it's called dynamical friction. And in this case, there's something similar that happens. Here, there's a language that is more common if you think about atoms, which imagine that you have a binary moving inside this very dense boson cloud, right? Boson condensate. Basically, you're pumping energy in this state. Think about what you know about atoms. Your atom is for a given state, you're at a given energy level. If you put a lot of energy on this level, you might ionize your atom, right? So here you have something similar. So you can actually basically ionize your condensate because of the movement of the binary. And so the last part is really, that's what actually I've been mostly working on in the last 2-3 years, which is actually using something called extreme mass ratio in spirals, which are systems that LIGO will see in principle, which are systems where you have extremely asymmetric masses. So think about 1 million solar mass black holes, a smaller one with 10 solar mass black holes moving around it. And what is interesting about this system, so LIGO will, in principle, it will be one of the sources that LIGO will see, and it will see it for months to years. So these will be systems that will be there forever, like for a very long time in the LIGO band, which means if you follow this gravitational wave, any small disturbance that you see, you will be able to pick it up and make measurements very well, and for example test gravity extremely well, but also the presence of any environment around your black hole. One challenge, and that's why people have spent so much time working on this, is that this is extremely difficult to model. I have a couple of slides here, but I'm going to give the punchline to not keep you here forever. That's what we've been working on, which is essentially considering this system inside these clouds. The way you do it is through perturbation techniques. and use the fact that you're talking about a big black hole and a small black hole. And that basically allows you to have small parameters in your system. So the mass ratio is a small parameter in these systems. And so you can solve Einstein's equation perturbatively, basically, as in powers of the mass ratio. But to do mathematics and use, again, to go back to the simplicity of black holes, to actually use the fact that if I do everything on top of a black hole, on the Kerr spacetime, things are simpler. I can also use the fact that in general, if you make the math, the density of these environments is actually, in terms of, it doesn't curve much the spacetime. The curvature of spacetime is mostly basically settled by the black hole. So you can also consider your environment, so in this case this cloud, as a small perturbation on top of Kerr. If you do that, you can actually solve the equation in a very not simple way, but you can actually do or solve this problem, which is what we've been trying to do. Without these techniques, probably this problem it cannot be done. Basically, it's way too hard. So this shows a plot where we basically have a small black hole moving inside this cloud, and you can see these perturbing basically the environment, and these perturbations lead to gravitational emission, but not only gravitational emission, but what I said about ionization. So basically, part of this boson cloud is basically being ejected because of the movement of the binary. Well, I'm just going to explain this plot because in terms of observations, what this means is because your orbit will decay in a different way. So the orbital, as you orbit, you're in vacuum, you only have gravitational radiation. That's the only thing that can make the orbit shrink, because you know that in Newtonian mechanics that doesn't happen. In this case, you have an additional channel of dissipation, which is basically the scalar radiation. And so in terms of observation, it basically means, you cannot see it very well, that if you have two waves that initially start very close together, one describing the wave from vacuum and one describing the wave in the presence of the environment, these two waves, because the speed at which the orbit shrinks is different in the two cases, the two waves will start to be dephased from each other. That's what basically you will detect in your detect. And memories are extremely important here because you can see these waves for a very long time. So even if the effect is small locally, if you see many cycles of the orbit, you can start seeing these dephasings. So we did some job, and that's a nice slide, I swear, where we simulated this Emery plus cloud in Lisbon. That's an example, just to show the example, where we can actually measure the parameters extremely well. So here you cannot see it very well, but it's 10 to the minus 17. So this is the injected value for this field. And the error here is 5.56, 5.5. So the error is around less than 1% in terms of the measurement. So it's an extremely precise. You're doing basically almost particle physics with this. Of course, things are more complicated than that. Yeah, there's environments, there's equation disk, etc. So this will also change the orbit, and whether you can distinguish all of this is work in progress. So I will finish here. With this last sentence, the rest you can read, which, as I said, so I'm doing all of this because LISA will happen, there will be all the detectors, and they will start doing precision physics. But once you become extremely precise, it also means that you need to be extremely precise in your predictions, right? So that's the difficult part. And besides that, the more precise you become, the more events will be detected. And just that is a big challenge, right? Imagine doing data analysis not of one event, but a bunch of events together at the same time. So that's will be one of the biggest challenge of the next 20 years. Thank you.